Good afternoon. And yeah, I haven't been here for a while. I was here 2 weeks ago, or 3 weeks ago, or was it 4 weeks ago? I can't remember anymore. Time passes. So just to remember what we talked about, I mentioned the fact that artificial intelligence is part of computing science, and like many other subfields of computing science. And within AI, we have something called machine learning. Same time as other subfields as well of AI. And within machine learning, we have supervised learning, unsupervised learning, reinforcement learning, and so forth. And within supervised learning, we have many methods. One of them is deep learning. The point that I wanted to make is that despite the fact that many media are trying to, they don't convey this message properly, and they make you believe that deep learning is like AI, is like machine learning. They're the same, but actually one is included in the other. Okay. So deep learning is part of machine learning, which is part of AI. What we also talked about is the resurgence of AI today, because it's not new, it has been around for a long time. And I told you that the reason why now it's coming back is because we have a lot of data. We have amazing machines that we didn't have before, and we have new techniques, or techniques that we used to have before where we couldn't run them because we didn't have the machines and the data. The second session, I talked about precision health, and I showed you how machine learning can be used in medical applications, and particularly for precision health. And I mentioned the fact that it's not just for genomics, but it can be any other medical data that you can use to personalize treatment. Okay. We also talked about achievements of AI. Many incredible achievements. It's actually flabbergasting. Wow, all these machines that can beat the best of the best in the world. Okay, so what I want to do today is zoom in one of these bubbles here, particularly supervised learning, okay? So that you have an idea about how it works. I just told you there's this magical box that can do these things, but how does it actually do it? You will see that actually it's not that magical. Okay, so what is machine learning and what is particularly supervised learning? I often use this metaphor where I have a pile of balls of different sizes, different colors, different shapes. Not shapes, they're all spherical, they're balls, with different structures, with different weights, whatever. Okay, and I'll ask a child to sit there, watch me, what I'm going to do. I have buckets, okay, the buckets apparently have different colors, the same size, same shape, but they have different colors. And I take a ball, I look at it, assess it somehow, and then choose to put it in a bucket. Take another ball, assess it, evaluate it, and then put it in another bucket. And the child is watching me, learning what I'm doing. Because eventually I will ask the child, okay, now it's your turn. And the child will have to do it. So what the child is doing, the child is observing me and building a model. Trying to understand what distinguishes one ball that goes to this bucket and one ball that goes to the other bucket. And the day I say, okay, now it's your turn, and give them the ball, if they do it right, it means they build the right model that distinguishes the different balls. Actually, what happens is that probably the child will realize that the weight is irrelevant, the texture of the ball is irrelevant, the size is irrelevant. What matters is actually the color, and the black ball will go in the black bucket, and the green ball in the green bucket, and so forth. So they build a kind of a rule. Okay? That's what the machine will do. So the machine is doing exactly like the child, observing some cases that I will label. So when I put that ball in one bucket, I actually labeled it. I said, it belongs to that bucket. So the machine will see some cases that are labeled by an expert, okay, and learn a model, and then use that to do the same task. Okay, so what we have what we call a training set, a training data, that are all labeled. Here the label is a color. And this is an object. It can be, I don't know, a patient, it can be a ball, it can be an email, it can be anything. Okay? And later I will have other objects from the same domain that haven't been labeled, so they haven't been seen before. Okay? And what happens is that the computer will go over these and find a way to represent what discriminates one class, we call them a class, one label from the other, and build a model. Okay, I'm representing it here as a cloud, fuzzy cloud. So let's put a face on it. So now I'm going to use that cloud to automatically predict what label should each one of these have. Because I learned it from observation. I learned it from an example. Okay? I'll use analogy to do the same. That's what we call classification. It's actually prediction. I'm predicting what the label should be based on what I learned before. Machine learning is actually that. Okay? This is a very high-level description of machine learning. Of course, it's not as trivial. There are many issues, there are many challenges. For example, what are the features here that are relevant to distinguish between the different classes? What is the best algorithm to go over this and optimize it and build a model? And actually, how do I represent that information, that model that I put here as a cloud? How do I represent it in the computer so that I can efficiently use it here? So how do I effectively use it afterwards to do this prediction? I didn't explain all these, obviously, but at the high level, this is what machine learning is all about. And we use it for many things. So, for example, you heard of the autonomous vehicles. How does the computer on this car distinguishes between this road sign and that road sign? This is a stop sign, this is a one-way, or this is no parking, or all these signs. Well, we show them enough examples, and then they build a model, and then they learn. How do I distinguish between a pedestrian crossing in front of me and a plastic bag that the wind is flying? Okay? I build a learning model like I just showed you before. Handwriting recognition. Same thing. How do I distinguish between a 3 and a 2 and a 5 and a 6 different handwritings? And especially if you have numbers and letters, is it a B or is it a 6 or is it a 2 or whatever? So we use machine learning. Actually now they're even more sophisticated because I can take handwriting formally in math and I can understand and reproduce them in nicer font. You have it on your phone as well. You can write letters like this and then they are recognized regardless of the handwriting that you have. Other examples, we use them for spam detection. So the labels are actually your behavior. When you get an email, if you read it and answer it, it's obviously an important email. If you dump it without even reading it or barely read it, then maybe it's not that important. And after a while, the program will learn a model, your behavior, because your behavior is different from another person. What is spam to you may not be spam to somebody else. And it will build a model that discriminates between the spam and non-spam and will remove it for you automatically. You don't have to worry about it. Okay? Detection of fraud with different kinds of transactions, credit card transactions, financial applications as well, recommender systems. I'm going to go quickly here, otherwise I don't have time to cover everything. There are things that are even more sophisticated. Who's on Facebook, for example? Who's on Facebook? Yeah, I'm on Facebook too. So we may have many, many friends, between quotes. They're all active. They're all posting things. There's no way you can read everything on your wall. So what Facebook does, it looks at your behavior, what you shared, what you liked, what you commented on. Those seem to be interesting to you. Those that you didn't even bother about, they're not important. So after a while it builds a model and it learns what you like. So it will select and show you on your wall things that you likely react to. And the others, you will not see them because it's too many. Okay? There are even sophisticated remote controls for the TV. It knows the channels that you like watching and the channels that you don't like watching, so it skips these channels automatically. I don't know if I told you about this hat for people who are paraplegic on a wheelchair. You can control the wheelchair. So these learn automatically by looking at examples and build a model, and then it uses that model to do prediction. And I talked about many applications in healthcare the last time we met together. So how does it work? I have a patient, for example, here, new patient. I have some record, some information about that patient, and basically I want to know if this particular disease that I'm treating will reoccur or not. Okay? I want to predict it. It didn't happen yet. So what I do, I look at historical data, other patients, for which I have the information whether that disease reoccurred or not with this data, these treatments and these analysis and all that stuff. What I'll do, these are my observations. This is the class label. This is like the color of the buckets. Okay? I will learn a model, and then I will use that model to predict for this particular patient. Yes or no, it will reoccur. Does it make sense? Okay. Any question? Of course, I explained it at a very high level. There are many issues and many different, there are variations in the applications and well, different cases we're dealing with. And we name them differently. For example, here I have many possible classes. We call them a multi-class classification. So the model that I will build, it will predict for many classes. In many other applications, like spam, non-spam, I have only 2 classes. This is what we call a binary class classification. So my model that I'll build deals with only 2 classes. And most algorithms will deal with that. There's also, when we do the prediction, I have new objects that I didn't label before. And when I use my model that I learned on past data, for each object, I will predict one label. This is called single label classification. So each one will get a single label. But there are cases where I may predict more than just one label. Okay. For example, these are documents, and I want to predict the topic that is being discussed. Well, we may discuss different topics in one document, not one. Or these are images, and I need to predict what's in that image. Is it a cat or a dog? Well, you may have a cat or a dog at the same time with the same image. Okay, so you have different labels. This is called a multi-label classification. There's another issue, very important, particularly for people in medicine, but many other applications as well. This is the notion of black boxes and interpretable models. So here, the model, that cloud that I used before to represent the model, that cloud is actually black box. It means that I don't see how it is inside. It predicts, even almost perfectly, at 99% accuracy, but I don't know how. If I ask it, why did you say it's blue or red? It doesn't tell you. There are other models. When you learn the model, actually you can see inside. You can see a representation that makes sense to us. So when it predicts, for example, that this is red or this is green, I can ask it why, and it may show me some rules that it's used to get to that conclusion. So why this is important? Because, for example, in medicine, if you say this patient should get this treatment, I'd like to ask why. And if it's a black box, it will not be able to answer me. You say, just that, use that treatment, that's it. Trust me. Will you? Will you trust it? The other cases may say, well, use this treatment, say why? I'll say, okay, because this patient is 15 years old, and this patient has this treatment before, and whatever. It gives you some kind of facts that could be used to justify. So not only you can see, but you can actually also change them. You can improve the model, because this model is based on the examples. But the practitioner, the doctor, may know other things that are not represented in the examples. So may enrich the knowledge in the model when we can see it. There are other important issues as well. Often the approach is assuming that the data, here I have two classes, the data that is given for training is balanced. I have as many greens as I have red. Okay? And then I build my model. In reality, I have cases like this. So I have a lot of representation from one class, or we call it a majority class, and then I have rare cases from another class. This is the minority class. And then yet you have to learn from it. But what happens is that if you don't take into account the fact that it's imbalanced, the majority class will overshadow the minority class. Okay? And you think you have a very accurate system, but actually it's not, because it's biased towards the majority class. But what you need to remember is this picture here. I have as input data that is labeled. I learn, and the learning will give me as output a model that represents the different classes here, okay, based on this data. Then it comes a time where I will use this model and some evidence that I have that I don't know what label it is. Then I'll do this prediction, and the prediction consists of putting a label on that observation. Okay? That's what supervised learning does. And most of the applications are using this, and this is what is making the success of AI today. Any questions? Okay, so typically what happens is that you have data that has been labeled. It's very expensive because you need an expert sitting there and labeling them for you, or we need time for you to behave until we get enough observations, like deleting enough spam from your mail and reading enough emails, or reading and commenting enough posts on Facebook and so forth until we get enough data. So this data is typically expensive to get. It takes time and effort. But once you have it, what we do typically, we split it into two parts. One part, the bigger part, is used for training, like I explained before, and one part is left for testing. So once I have the model that I learned from the training data, I will use the testing data after hiding the labels. I hide the labels. I use the model to evaluate the testing. The model will give me new labels. I'll compare them with the labels that I hid, and if they are the same, then I'm accurate. Okay, so I will estimate the accuracy. And if the accuracy is good enough for my application, then I will deploy it. So then I have new data that is not labeled, and I happily use my model to do the prediction. What does that mean, that the accuracy is good enough for the application? Because in some applications, you can afford to make mistakes. So if I have some emails that are spam, but they're actually still appearing in my email list, well, it's annoying. It's not life-threatening. Okay. So an accuracy of even 70% is still okay. I'm not going to die. But when you talk about turning on or off a power plant, you need a very good accuracy. When it comes to giving a treatment to a patient or doing some diagnostic, the accuracy has to be very high. Okay. So when do you deploy this model? It depends upon the application. So what I wanted to talk about today is how do I, so how do I do this training? Okay. And I will show you some examples of approaches. So basically I'm going to open the box and show you how it is inside. And there are many, many methods to do it. There's, I'll talk about, I'll probably talk about just about these two. I'll skip this one. But there are many others. They're completely different, but their goal is the same. I have some data that is labeled. I go over that to build some model that will be used later to automatically label data that hasn't been labeled. Okay. They don't have the same representation of the model. That cloud that I represented, each one will represent a different one. Actually, I will start with one that doesn't have that cloud whatsoever. It's called k-nearest neighbors. It's very naive. We call it lazy learning. It doesn't learn anything. Yet it actually gives you that output, often with amazing accuracy. So what does it do? So basically, let's take the example of, I don't know, let's say giving a loan to a client coming to the bank. I have to decide, should I give the loan or not? So that's the prediction. Yes, no, 2 classes. And I have this client. What does it mean, I have the client? Well, I have information about this client. The past, what kind of job, do they have a car, do they own a house, or do they rent, where do they live, all that stuff, all that information. So in order to make that decision, a very easy approach would be to take the record of that client, look at my history. Is there somebody that has similar file? And the closest one to that one, I'll look. Did I actually give them a loan or not? Did they pay back or they defaulted on the loan? And I'll make my decision like this. Does it make sense? Okay. So this is called the nearest neighbor. In other words, I look at my data that was given to me for training. I'm not training at all. I'm just leaving it aside. And whenever I have that decision to make, I'll take the record and I'll look at the nearest neighbor. Who's the nearest to it? And I take that label and assign it. So here's my new entry, my new record. I don't know what color it should be. Color is the decision, basically, yes, no. I have this data from the past. So for example, this one paid back, defaulted, paid back, defaulted, paid back, for example. Okay. Then I get this new entry. I will have a distance function that compares records. And I go through here and find the closest one. Aha, this is the closest one. Then I will label this one with the same label. Okay. I didn't learn anything. But it works because it gives me as output what I want. Okay. Now, whether the accuracy is good or not, it has to be tested. There's a variant called k-nearest neighbors, where instead of taking the closest one, I'll take the k closest one. K can be 10, or 4, in this case I have 5. I take the 5 records that are the closest to the one that I need to label, and I ask them to vote. Oh, it happens that I have 1, 2, 3 that are red and 2 that are blue. Well, I can give the label of the majority. Okay? Make sense? Very easy, straightforward, but naive approach. The vote can be equal for all of them, or it can be weighted, so some have higher weight or whatever. There are different variations, of course. This is the high-level description. Okay. Any questions? No? Gee, last time you were talking a lot. Maybe because he's here. I'll skip the decision tree one because we don't have time. I want to tell you a little bit more about the neural networks, because this is the method that is very popular, and it's the ancestor of deep learning. But it has been around for many, many, many years. It actually started in the 50s. The idea is to copy or mimic what happens in the brain, even though we don't exactly understand what happens in the brain and how. But we have many different kinds of neurons in our brain and nervous system. And the neurons, basically, they have these dendrites around this cell. They receive information, and then at one point that cell decides to shoot a message along the axon to other to other cells, and they communicate like this. In the brain, we have 100 billion neurons like that. We have many, many, many connections. It's amazing. It's not like the machines we have today, but the machines are getting denser and denser. Okay, but still, the brain is by far many orders of magnitude more complex than the machines that we have today. However, the machines we have today are way faster. The amazing thing with our brain is that it's massively parallel. All these neurons are activated at the same time. Okay, so how does it work? So basically they came up with this idea of an artificial neuron, and I'll show you what it is, and then they put these neurons in layers. The first layer receives the input. So for example, the record of the client coming to the bank. Okay, and then I have a set of neurons that represent the output layer. The output layer will tell me the label that I'm trying to predict. Yes, this person should get a loan because they will pay back. No, this person should not get a loan because they will default. Okay, for example, so two classes. And then I have hidden layers. And the neuron, these artificial neurons, are connected one layer at a time. So the input layer is connected to the hidden layer is connected to the output layer. And then I have many hidden layers. But in the past, because the computers were not that powerful, we couldn't afford to have many, many layers. We had just one layer, and most people actually worked with just one hidden layer. Okay? And what happens is that from the input, I have an input that I describe as a vector. That vector is passed to the first layer, and then from the first layer, the information, the message is propagated to the hidden layer, and then from the hidden layer propagated to the output layer, and then I can read there the prediction. Of course, every single node here is not necessarily connected to every single node in the next layer. There are different ways of building these architectures. What do I have? I have weights on all these connections. So the connections are not the same, they have different weights. And basically what I'll do, the learning is, I will pass a record without its label, and then I get the output. I will read the output, that's the predicted label. I compare it with the label that I wanted to predict. And if they're not the same, there's an error, I will propagate the error backwards to adjust the weights. And I'll do that again, and I'll do that again, and I'll do that again, thousands and thousands of times, until it converges towards the prediction that I wanted. Then I stop. And when I stop, what do I have? I have different weights. So the learning is actually weights in these connections. Then later, when I trust it, because I tested it and all that stuff, I have new records that I haven't labeled before, I haven't seen the label, I pass them through here, the information is propagated, and I get the prediction down the road. Okay, so the similarity between an artificial neural network and the natural one, actually they're very close, except we don't know exactly what happens in the soma here. So you have these dendrites, and you have the cell, and the dendrites receive a message. At one point, this cell decides, okay, I'll send the message, and the message will go to all the dendrites and so forth. Here, what do I have? I have an input vector, and actually a weight vector as well. And so the cell here will sum all these weights received from the different neurons that come from the other layer. And there's some bias here, and at one point there's an activation function that decides, okay, I'll fire a message, and the message goes to the next layer. So in principle, they look very similar. Yeah, so this is what I was telling you about. The edges basically here have these weights, and learning consists of finding the right weights. Okay, by passing, so there's a feed forward of the message, and then I compare the labels, I see the error, I back propagate the adjustments. And I'll do that in thousands and thousands of times until it converges, then I stop. stop here. Yeah, this is exactly what I was explaining. So I have this label here that I hide. I take these ones, I pass them through here, and then I reinforce the weights by, well, I adjust them once I know the error. These neural networks have an amazing accuracy. When the neural network is designed properly, but it's an art how to design this neural network. It's very robust even when you have a lot of noise in your data. The problem is that it takes a long time to train. Once it learns something, and even though it has very high accuracy, when you ask it, hey, why did you label it this way or that way? The only explanation it has is, oh, because I have this weight and that weight and that weight. It means nothing to me as a human being. So it's very difficult to understand if there's any reasoning behind that labeling. So it's a black box. It's not easy to incorporate domain knowledge. If there is domain knowledge that I have as a practitioner that is not represented in the training data, I cannot add it. Because adding it means changing the weights. But if I change one weight, the repercussions are uncontrollable. Okay? So I can't really inject knowledge. And as I said, the design is an art. How to design these networks. Yes?
So if it's a black box,
yeah.
What decides that it gets propagated backwards, like that error message?
Yeah, so I compare the label that the neural network gave me and the label that I was expecting.
Yeah.
Okay, because it's training data, I have the label, I hit it, I pass the information, and then I compare the two. And if they're not the same, I can calculate the error and I propagate it back and say, oh, I changed from I wanted this label to come out. So here are the changes that I need to make in these weights. And then the next layer will say the same thing. Oh, these are the changes that I have to do. These are the changes. Until you change all the weights.
So the reason it's a black box is because you don't know why these weight changes are being made within.
No, when I use it, and it's a black box, when I use it,
yeah.
The weights were learned already.
Okay.
So there's a process of learning. Once it converges and it learns, I keep it as is, fixed. I use it. Here's a new object that I don't know the label of. And then it'll tell me the label. Then I'll ask it, hey, why did you give me this label? It'll give me that label because of these weights that it learned before. But the weights don't mean anything to me. That's why it's a black box.
So, another?
Okay.
Yeah.
I'm just confused about, like, what's the difference between the different nodes within the same level? So like the two gray ones, like between those. So there's different weights, but are they like different labels?
So the nodes are the same. They have the same activation function, typically. But they have what we call a bias. They may have, so in addition to these weights, each node has also a bias that it adds in the summing of the input. That's how they differentiate. We differentiate them. That bias is also learned, so I can change it as I'm propagating the error backwards, back propagation. What's the difference between these nodes and these nodes? They are the same kind of nodes, except these ones are input. They receive information from outside. And these ones, they don't send message when they give you the output. But
so
there's no difference between this node and that node.
Okay.
The only difference, again, is the bias and how many links come to them.
Right.
So this one is connected to these three. This one is also connected to these three in this representation. But in a large network, I may have this one receiving the message only from these two, and this one receiving it from these three. So how the vector that is coming to them as input may not be the same.
Okay.
But they have the same activation function.
And then like the bias is based on the output they end up getting and like the propagation.
Okay, so in the beginning, when I start the network, I didn't teach it anything yet. All these edges have a weight, and all these nodes have a bias, what we call a bias, which is here. So they have weights, and they have a bias. Okay, I will start them randomly. They are started randomly. I don't know what it is, so I just give a random number. And then as it learns,
It adjusts.
they adjust these.
Okay.
They adjust the weight and adjust the bias. Until it converges. What does it mean it converges? Either I run it a certain number, fixed number of times, like 1,000,000 times, Or I say when the error is becoming very small, I stop. Or the changes that I'm making are not having any impact anymore, I can stop. And once you stop, you use it as is. Okay? So what I just described is now called as deep learning. The only difference is that instead of having an input layer, one hidden layer, and output layer, with this representation that I showed you, so each cell has many inputs with different weights, and then sums there's an activation function. The difference is that now I may have many hidden layers, because the machines that we have today allow us to do sophisticated structures like this, and because it has many hidden layers, we call it deep, hence the deep learning term. Of course, here in this representation, every single node is connected with every single node in the previous layer, and then connected to every single node in the next layer. This is fully connected, but we have many different architectures. Okay? For example, we have some that the hidden layer actually becomes smaller and then bigger, and all that stuff. There's so many different architectures, and really an art to do that. And this is what we call convolution neural networks, recurrent neural networks, and so forth. It doesn't really matter much in this class. So anyways, but this is today the most effective way of teaching a machine to discriminate between classes. So this is what is used in the chatbot that you have on your phone, or the self-driving car, or whatever application. Any question? Now I can move to something more exciting. This is just to give you an idea about how these machines are learning. Okay. And remember in the first lecture, I was telling you about how these techniques are now used to distinguish what's in a picture. Is it a dog, is it a cat? And I showed you examples where actually it's terrible. Any child will be able to distinguish between, for example, the mop and the dog. Well, these methods are not good enough. But at the same time, they beat the humans at many other applications, like detecting melanoma or mammography, to detecting breast cancer. These techniques are better than most doctors. Yes?
Who puts each node in the hidden layer? Like, is that done manually?
Yes, it's designed at the beginning. There's a design of an architecture, and then you teach it.
And those are any possibility that it could be, say, example, if it's a photo and it has to distinguish who's in it, that would be like any single kind of person.
So
plant,
the input,
yeah.
the number of nodes here depends upon how you will code your input, the data that you have.
Mm-hmm.
So the input here, the number of nodes that you have, is dictated by the kind of input you will give it. You will describe it as a vector and you'll pass it here. The output layer is also dictated by the kind of output you expect. Is it a binary classification, so 2? So 1, 2, span, non-span? Then you don't need 4 nodes for that. You need actually only one node will tell you if it's 1 or 0. Okay? But if you have many labels, then you need more nodes. So these, the 2 layers, are dictated by the kind of input and output that you have in your data. Here, that's an art. You have to design it somehow. Okay. By the way, here can be text. For example, have you used your phone and you're typing, and as you type, before even you finish the word, the phone actually predicts this is the word that you're going to write, and it suggests some words. Okay. They learn from past text written in English, in the language that you're, because they detect the language that you're using, and from another corpus, they predict which word comes after which word, and then they know, here are the suggestions that I can give you. In that case, the output They are actually sequences of letters or sequences of words. So it depends upon the application you're dealing with, the way you design this. You said, who does that? Well, there is a design of this, and it depends upon the application you're dealing with. The neural network that I will use to predict the words that come next, to do translation or to generate an answer for the chatbot or whatever, is completely different than a neural network that is predicting is it melanoma or no, not melanoma. But the learning process is the same. Yes?
So would this be applied to medicine then, even though it is a black box?
Unfortunately, yes.
Yeah?
So this is what is used today. I'm not a huge fan of it. I prefer other methods where you can ask it why, then it'll explain. So many people are working on techniques that come on top of this to explain why. So where is the attention happening when I'm detecting that as actually it's a melanoma? It'll show me in the image where it's actually focusing on. That's one example of explaining. Now, what is explanation is kind of fuzzy, and there's a subfield within AI called XAI, or explainable AI. We're working on trying to explain this. And there are other people who are working on other techniques that are not black box. But unfortunately, they're not as accurate as these. So they're black boxes, but they're very accurate. The others are not black boxes, but they're not that accurate. So we're trying to find the balance.
And it's applied to imaging, or what is it?
Apply to all sorts of things whenever you need to predict.
Okay.
And whenever you have data that is labeled to provide it to learn. Because if you don't have data that is labeled, it doesn't know where to learn. Okay. Maybe you should turn it off.
Yeah.
Use more break, I'm gonna change